Okay, so we are looking at kinetic reactors today. Last week, we looked at the more simplified reactor models, R gives, R yield, R stoic, all those ones, right? R equilibrium. So we want to go into the ones that require a little bit more details, the ones that would involve some kinetics. And we are all familiar with reaction engineering, so we would just fall on the knowledge we already have. Now, a few things to just keep in mind when we are using Aspen. So, you see the units over here. These are the units that Aspen is going to be working in. The reason why we have to know these things is that if maybe you are trying to do a simulation and you are using information from literature, the units may be different. So you can't just put in the units as they are, right? So you need to do some kind of conversion. And it's specifically when it comes to the rate constant, our K value. So that's one thing to keep in mind. If we are doing it based on concentration, or if we are doing it with concentration being our driving force, then our focus is on this form of the equation, right? So we are using kilomole, meter cube, and then per second. If we are doing it based on pressure, with pressure as a driving force, then we need it in this form. So even in our discussion today, you will have an example like that. I think for that one, the unit was in mole per meter cube ATM per second, per ATM per second. Right, so we'll have to change it to kilomole, and then we'll have to change it from ATM to Pascal. So these are some of the things to just keep in mind. And these are for homogeneous reactions, right? If we are having homogeneous reaction, we use these ones. If it's heterogeneous, then we use the ones we see below, the ones that include the weight of the catalyst. Please, is that okay? So we need to know the unit so that we are putting in the right values when it comes to the simulation. Okay, so that's the first thing that we just want to keep in mind. And we're already familiar with the design equations when it comes to working with some of these reactors. So we are going to start with a CSTR. Right? So we know the material balance and the rate equations and then the energy balance equations. So we already know these things. Okay. When it comes to specifying a continuous state tank reactor, some of the things we'll need to put into Aspen will be the volume of the reactor, the pressure, then the reactions and their rate laws, and then the Arrhenius parameters, and then the temperature or maybe the duty. So you can work with either of them, right? So these are some of the important details that we will need when we are specifying our CSTR. Please, in the course of the discussion, if there are questions, you can just stop me and ask me. So we'll try to use an example to really get the concept, how we do the specifications. Okay. So the first question says that the irreversible endothermic vapor phase reaction follows an elementary rates law. So we have our equation there, and we are told that the feed is fed to the reactor at a rate of 10 mole per minute and a pressure of 2 atm to a CSTR of volume 500 liters. The entrance temperature of the feed is 1100 Kelvin. So we just want to try and model this, and then we'll look at the conversion, the exit temperature, and we'll do this when it is first adiabatic and then when it is isothermal. We've been given the expression for our K, so we'll talk about that very soon. But one thing, so what was put here, right, from what we specified, from what the note specified, it was acetone instead. And if you check it, realize that the carbons are not balanced. So if you first check the balance, realize that we have two carbons on the left, but we have three on the right. So it was supposed to be acetone instead. You see three on the right, right? So we'll be using acetone instead. Then this one here is ketene, and then this one here is methane. So I'm just letting us know so that when we get the notes, we understand why we use what we are using. Okay. So as usual, the very first thing we would do is that we would specify or would put in our components, the things that we are going to be using, reactants, products. If there are any inerts or intermediate products, we include them as well, right? But for this one, we are just looking at a reactant and then some products. So for the first reactant, we have acetone, and then we have methane. That's our product, one of our products. And then we have ketene. So that's the CH2CO, right? So that's ketene. So I can even change the name here. Okay. Then the very next thing we want to do is that we want to specify a property method. So I think for this one, we can go with Penn Robinson. Let's see. Okay, they use NRTL, so let's go with NRTL. And then we can run the simulation and continue from there. Okay, so our results are available. We can pick it up from there. So we'll have our feed. For this one, we are just focusing on the reactors. So we are not looking at any other process. We'll have our CSTR, and then we'll have our product stream. So let's connect everything. I'll just label this as feed and products. Okay. So the first thing we'll do, as we always do, is to specify our feed stream, right? And for the feed stream, we are told that our feed is fed in at 10 mole per minute. So we can place that here, 10 mole per minute. We have the pressure to be 2 atm. And then we have the temperature to be 1100 Kelvin, 1100 Kelvin. And for that one, it's going to be pure acetone. We're told that was a pure feed, right? So it's pure acetone. So we can make the mole fraction here 1, or we could have specified the mole flow from here. So here the mole fraction for acetone will be 1. So that's just for the feed. Then we can come to the reactor itself. So what details do we need? So this is where the new information to us will come up, how we can work with these kinds of reactors. Now, if you are using version 14, you would see this. If you are using the earlier versions, it would look like this instead. So let me make this larger. So it will just look like this instead. So if you are using the older versions, right? But then it's the same idea. The only difference that we are seeing is that for version 14, they are asking if you want to work with a conceptual mode where you are just using the shortcut calculations, or you want to give a few more details on things like the jackets, the coil, all those things. So that's if you want to get into those details, right? So we'll keep it on conceptual mode, and then we'll just put in the details we need. So we need the pressure, we need the temperature, or the duty. So the pressure is 2 atm. We are going to start with the duty because the first part is we're operating adiabatically. So the duty would be 0. One very, very important point is what comes after the valid phases. If you do not choose your correct phase, you may not end up having the reaction you are looking for, right? So there are times that the question will state it's a liquid phase reaction, and we forget to change this from vapor only to liquid only. If you should do that, you won't get what you are looking for. So kindly keep that in mind. Here, we are told that it's a vapor phase reaction, so we don't have a problem. We'll just keep it as vapor phase. Under the specification type, you would see that we have different options. So you can decide to specify just the reactor volume, the residence time, or maybe reactor volume and phase volume, a combination of things. So we will keep it on reactor volume because we have the reactor volume. But let's say you were dealing with a system that had maybe 2 phases, right? There's a liquid phase, there's a vapor phase, and you want to specify the phase of one of them. So you could have selected that. Oh, okay, okay. If I have to do this, I'll have to add another outlet. But let me do that just to show us, just so that we understand what I'm trying to say. I'll delete it afterwards. Valid, I have to change this as well to vapor liquid. Okay. So I can now specify that maybe for this particular phase, maybe for the vapor phase, this should be the volume, or for the liquid phase, that should be the volume, the condensed phase. So you can do any of these things, right? Depending on the information you have or the kind of system you have. So keep it at vapor only, and then we can delete that extra string. Okay. So what's the volume from the question? It was 500 liters. We'll put in the 500. This is reactor volume. So we are done with that. Now you notice that specifications are all fine now. We need to make some inputs to the kinetics this time. Right. So when we get here, this is how it's going to look like. If we are dealing with a crystallization process, you could have selected that and then you now model that. We are looking at just a normal reaction. So there are two ways we can go about placing in a reaction in Aspen. You can do it from the block by clicking on new, naming the reaction. So we'll just leave it as R1. and then choosing the type of reaction. So under the types, we have different ones. We have emulsion, fermentation, free radical. That one is usually for polymerization. General means that you are going to be the ones to put in all the information, right? Then we have ionic, LHHW. That's usually if you have some kind of um catalyst and all those things. Power law, we should be familiar with the power law by now. For, I mean, we've done chemical reaction engineering. Pyrolysis can be modeled, segments-based step growth. These ones are usually also for polymers. So we have so many options. But then if you look at what the question said, the question told us that it's an elementary reaction, the elementary rates law, right? So we can easily use the power law to model what we have. So we'll select power law. Now you realize that the reaction is here, R1. Another way we could have gone about it is we could have come down. So if you look at the far left, the simulation pane, you could have come down, come to reactions, clicked on new, and then specified your reaction, right? The same procedure. So you click on new, enter the reaction ID, select the type of reaction, power law, click on OK, and then it will be done. Now, once we are done selecting the reaction, or once we are done choosing the type of reaction we want to use, we'll double click on it, and then we'll now put in the relevant equations, the reactants, and then the products. So we have our acetone forming methane and ketene. And then the coefficients, everything was 1, 1, 1. Now, I'm going to ask us a very important question. I want to see who can answer. So why is it that for the exponents, remember we are dealing with the power law. Why is it that for the exponents, acetone is 1, but methane and ketene are 0? Anyone? Can anyone figure it out?
Hello, Tiago.
Yes, please.
Yeah, so I think with the power law, the overall rate of reaction is one. So the exponent has to be one, so that satisfy that condition for the overall rate of reaction or order of the reaction to be one.
Okay. So you also realize that since it's a power law, we have one reactant, right? If we were supposed to write out the rates of this reaction, so let's say we had, but thank you for your contribution. So let's say we had um our R is equal to a minus, oh sorry, this thing is trying to be stubborn. Let me do it down here. So R is equal to maybe a minus KCA. So let's say this was A, this was B, this was C. It will be minus KCA. We could have said that this was CB to the power 0 and CC to the power 0. I hope you agree, because the products, we won't have any, I mean, power for them, right? So we can make it 0 so that it ends up becoming 1. So we'll have minus KCA. This is that okay?
Yes, please.
Yes,
Okay,
please.
okay, that's fine. If we had a reaction where maybe this also was supposed to have a value, then you'd have included it in the exponent. You'd have put in a different value. So that's why we use the value of 0. Okay. But who answered the question when I asked?
No, it was Nathaniel.
Oh, okay. Nathaniel, thank you for your contribution. Okay. So now that we are done with that part, let's include the kinetics. So when we come to the kinetics tab, this is also a part that has quite a lot of details. You would see the reaction you have specified. If you have specified multiple reactions, you would see all of them there. So you have to choose them one by one and then do the specifications for them. The reacting phase, we said it's a vapor phase, so we need to change that. And the rate basis is going to be the reactor volume for a CSTR. If it was a catalytic CSTR, maybe there was some kind of catalyst in there, would have considered using the catalyst weight instead. But we are not dealing with a catalyst yet, so we'll just keep it on the reactor volume. Okay. Now, when it comes to specifying our K, our E, all these details, we'll need to do a little bit of modification to what we have from the question, right? Because remember that Aspen is considering what we have in a certain format. Okay. So if we look at what we have down here, we have K to be equal to exponential 34.34 minus all of that, right? But what happens is that it has to look like what we see over here. So Aspen has given us a sample of how it should look like over here. The K should be separated, or if we are supposed to express this, we should have a constant term separated from the exponential that contains the temperature term. So in the first, what we are trying to do is this. The calculation has been done here. Let me go down just a bit. What we are trying to do is that we are trying to expand this. So we make it exponential the first term and then exponential the second term, right? Because if I have exponential, maybe a plus b is exponential a times exponential b. So that's what we've done here, right? So we can now express this first part as 8.197 times 10 to the power 14. That's what Aspen is expecting for the k, that single constant value. Then the exponential term that contains the temperature is what we are going to manipulate to get our E, right? So how are we doing the manipulation? The minus 34222 over T is going to be equal to, sorry, the minus 34222, right, is going to be equal to E over R, because you're supposed to get minus E over RT. So the 1 over T is there. It means that the 34222 is the same as the E over R, right? So we multiply this by the R, and then we'll end up getting our E. And this was done to get it in kilojoule per mole Kelvin. For this one, you can work with different units. For the E, you can work with different units. For the key, the units have to be very, very particular. They have to be very, very specific, as we mentioned at the very beginning. So for the key, we can put in the value we just got, 8.197 8.197. And then if you want to say times 10 to the power 14, we just use E plus 14, right? Aspen takes it as times 10 to the power 14. Then for the E, we'll make it 284.522. And then this becomes kilojoule per mole. So kilojoule per mole. Now, the next thing is, if we have a T naught value, we add it. We don't have a T naught value here. So I'm talking about if we had a reaction that looked like maybe K was equal to K naught exponential minus E over R, 1 over T minus 1 over T naught. If we had this T naught value, we would have put it in there. But for this question, we don't have something of that sort, right? And the other thing we'll say is that we see the CI basis here. Is our rate equation on the basis of concentration, molarity, or is it partial pressure, right? Or is it mole fraction, or is it mass concentration, or is it fugacity? So what is our basis? For this particular question, it's going to be on the basis of molarity, the concentration. So that should be fine. But then you can have situations where it's based on partial pressure, especially if you're dealing with gas phase reactions and there's pressure change here and there, right? So we can keep the molarity. So we are done with the specifications. We can run the simulation. And then let's come back and look at the results. So we'll check the results of the block first. Okay. So if we check the results of the block, we see the outlet temperature. Remember, we kept it we made the duty 0, so it was adiabatic, right? So we started at let's get the inlet temperature. We started at 1100 Kelvin, and now we're at 879 Kelvin. So the temperature has dropped, right? Okay, and it makes sense because we're dealing with an endothermic reaction, so it's supposed to take in heat. So the temperature is going to be dropping. Then we have our outlet pressure, we have the vapor fraction, we have all these details here. We have the balance, we have the kinetics, we have all the things that we need. So all these things are here. Then let's go to the stream results. That would be the parts that would be very important to us. So for the stream results, let me shift this back. Okay. So let's look at the mole flows. We can see that some methane and some ketene have been produced, right? And then some of the acid has been reacted. So we can calculate our conversion from here. Now, we were supposed to run it isothermally, like the second part of the question. We're supposed to operate it isothermally. What we would have done is that in the reactor, we would have specified the temperature to be the same temperature as what was coming in, so that it doesn't change. So it would be at 1100 Kelvin throughout. And then if we should run it, we would have our results. So we see that when it was isothermal, our results we had a much better conversion than when it was left or when it was endothermic. I mean, when it was adiabatic, right? This is that okay? And
Yes,
the idea
please.
behind it is that it would need to be taken in heat. And so for us to keep it under isothermal conditions, remember the temperature was dropping, we'll have to have some kind of heating utility or something to heat it up. So that added heat would end up pushing the conversion or end up driving the conversion. Okay. So I think we are done with this part. Yeah, we are done with this part. So we can move on to the next one. Okay. Now, for a PFR, we want to try the same example for a PFR, and then we'll look at how we can work with a packed bed reactor as well. So once again, these are just the design equations, things that we've seen quite often. Now, for a PFR, we'll need the volume of the reactor. So we'll need the length and the diameter because we are dealing with tubes now or something that is um usually tubular, right? And then we need the pressure of the reactor, the reaction, and then the rate loss again, the Arrhenius parameters, the temperature or duty. And then you can decide whether you're dealing with a single tube or multiple tubes, right? So you'd also need, if it's a packed bed reactor, you need catalyst weight, the density, porosity, the pressure, and all these other things as well. So we want to do the same example, but then this time we want to use a PFR instead of a CSTR, and they've given us a length to diameter ratio of 4:1. So the length to the diameter would be 4/1. And we know the volume of the cylinder or the reactor. Pi d squared over 4 is the area, and then h will be the length. So pi d squared over 4 times h will give us the volume, right? But then we said that h is 4d. So if we should put 4d in here for h, then we're just going to get pi d cubed. We can make d the subject, and that will be 0.542. And then h is 4 times of that, so that will be 2.158 meters. So that's just to help us find values we'll use for the dimensions of the cylinder. So what we'll do is that because we don't want to get rid of the CSTR, just like I showed us the last time, we'll duplicate the inlet so that we can just attach it to the PFR. So for the PFR, we'll choose our plug and then we'll place it down. Then we can connect our inlet and our outlet streams. Now, we'll duplicate this one over here. So let's come down here, the model palette, to come to manipulators, and we'll look for DUPL, the duplicate block. Then we can reconnect this to it so that it will duplicate the feed stream. It will just copy the values, and then we can use it in multiple situations so that we don't have to delete the CSTR, re-specify a feed stream, all of that. Okay. Now, we would have to specify the PFR itself. So we'll double click on it and then we'll choose the type of reactor. So we'll start with an adiabatic reactor and then we'll choose the configuration. But if we wanted to maybe choose a specific temperature, we could have done that as well. So maybe we should be constant at the inlet temperature, or it should be constant at a certain reactor temperature. Maybe the reactor temperature is not the same as the inlet, so we want it to be a different value. You can put it in there, and Aspen will keep it constant at that condition. And then we can also decide to specify a temperature profile. So if you should click on temperature profile, you would choose the location and then the temperature. So we'll start it from 0 to 1. 0 is the inlet, 1 is the outlet. So if I put in a value of 0, right, maybe the temperature at the inlet was, let's see, 1100 Kelvin. And then I know that at the outlet, so maybe, but let's see, halfway, I know that maybe it dropped to 800. And then I know that at the outlet, it dropped to, let's see, 600. You can do that as well, right? But then you have to be very, very careful with these things because if you should make a mistake, Aspen will give you so many errors. The other things we can also do is you can work with thermal fluids. And once again, Aspen is very particular about this. If you should select any of these, then it means that you would have to add a stream to represent your thermal fluid. So how do we do that? You notice that when I come to adding streams to the PFR, we have extra blue lines. These are for thermal fluids. They are optional, but you can add them if you want to. Right? So maybe a certain heating fluid or a cooling fluid, you can add them here. Then when you come into the reactor, you can choose reactor with constant thermal fluid temperature. coming. So let's say co-current or counter-current thermal fluid, and then you can specify the details, the U, the the outlet temperature of the thermal fluid itself, any of these things, right? The one I did earlier, I think I was supposed to get rid of these ones and then try that. So this is just by way of letting us know the different things that are out there that we can try, right? So you can also decide to use this one, constant thermal fluid. For this particular one, you don't need those inlet and outlet streams for the thermal fluid lines, right? You can just put in the values. But once you use co-current, counter-current, any of these ones, you need those streams. Okay. So we'll come back to adiabatic and then configuration. If it's a single tube, we don't need to worry about it. If it's multi-tubular, we'll select this and choose a number of tubes, right? If the diameter is constant throughout the length of the reactor, we are not worried. If it varies, we check that as well, right? So that we know that there's going to be some variation. Okay. Now the length, we're given, or we calculated the length to be 2.158 meters, and then the diameter was 0.542. Once again, vapor only. The process stream, very important. So it's vapor only. Then the reaction is just like what we did. It's the same reaction. So we'll just select R1. We don't need to re-specify. We've already done that. Right. So we'll just select reaction 1 and then we can run it. So let's check the results. Block results and then stream results. So we have the temperature, right? The minimum and maximum temperature in the system that we have. We have the residence time. Then we can also get the stream results. A minute. So we can see the stream results here as well. Please, is that okay? Is that fine?
Yes, please.
Yes, please. Okay. So I've already done the simulation for this one. I would send it to us after everything. But are there any questions before we move on to the next one? Because we've looked at um, I mean, irreversible reactions. We are now come to look at a reversible reaction. So any questions before we move on to that? Oh, okay, okay. Let's look at the profiles. So I didn't show us the profiles. So when we come to the plug flow reactor results, right, we can get temperature profiles, concentration profiles, pressure profiles, all of those things. So it's up here where we see plots. Let me enlarge this. Where we see plots. So I can click on temperature profile. But I can choose that if I had a thermal fluid, I could have looked at it in terms of the thermal fluid as well, but I'm just dealing with a process stream. Do I want it based on the residence time or the length of the reactor? You can choose that as well, right? So we would keep it on reactor length, and then we can just look at it. So throughout the length of the reactor, this is how the temperature profile is going to be. You have decided that you want the maybe pressure profile instead, so you could have done that too. So this time, let's use residence time. So we have the pressure profile. The pressure was constant throughout. So we didn't have any pressure drop situation. You could have modeled pressure drop as well. We'll look at that. We'll look at that too. But we don't have any pressure drop case here. So you can do different things. You can even do it for concentration, right? So there's composition, vapor fraction, all these wonderful things. So please, are there any questions before we continue? Any questions?
No, please.
Okay, that's fine. So if there are no questions, then let's carry on. Let's start a new simulation. So I'll close this one and we'll start a new one. Okay, so it takes some time to do, but will come soon. Okay. The next question. This time we're dealing with a reversible reaction. We are told that normal butane is to be isomerized to isobutane in a CSTR. Yes, so it's being isomerized in a CSTR to isobutane. This elementary reversible reaction is to be carried out adiabatically in the liquid phase. So this time we are in the liquid phase under high pressure of 20 bar, using essentially trace amounts of a liquid catalyst. That gives a specific reaction rate of 31.1 per hour at 360 Kelvin. So notice that has given us the a certain reaction rate value at a certain temperature. So this time we have a T naught value, and this is in per hour. Remember that the K values we should get should always be in per second, per what we started with. So we'll have to change it from per hour to per second. I'm just putting out a few points so that as we progress, we understand why we'll do certain things. The feed enters at 330 Kelvin at a flow rate of 163 kilomole per hour. 90 mole percent, so this for the feed, the composition of the feed, 90 mole percent N-butane, 10 mole percent I-pentane. If the volume of the reactor is 1 meter cube, calculate the conversion of N-butane and we're given some parameters. So let's start with our components. We have N-butane, we have I-butane, so our reactants and our products. And then there's isopentane in the feed as well, right? It's not part of the reaction, so but it is part, it's in the feed, so let's include it. So I-pentane. The reason I'm searching for it here is because if I try typing it out in full here, it wouldn't be able to fit. I tried it earlier and had issues. So I'll just search for it the traditional way. Okay, so we have isopentane. We can add it. Oh, what did I do? Did I add it twice? Sorry, a minute. Okay, so this would be our I. I'll just label it as I pens. Okay, so just rename. Then we'll choose our property method. So we can work with Penn Robinson. We are dealing with liquids. So normally when it comes to liquids, I really like working with NRTL, but well, we've already spoken about how to choose your property method. So you can choose the one that would be most convenient. So I would keep it on NRTL and then we'll just run it and then we'll see. Let's come to the main simulation interface. Then we can start the specification. So we have our inlets, we have our outlets, and we need our CSTR. So this is our feed. This is our products. Okay. Now for the feed, we are told that we have 160 kilomole per hour, right? That's our flow rate. So 160 kilomole per hour. We are given the pressure 20 bar, we're operating at 20 bar. And then the inlet temperature, we are told that the feed enters at 330 Kelvin. So 330 Kelvin. Then for the mole fractions, so we'll change this to mole fraction. We have 90% N-butane, 10% I-pentane. So N-butane will be 0.9, I-pentane will be 0.1, right? So we are fine with that. Then for the reactor, we have our pressure to be 20 bar. It's adiabatic, so the duty is 0. And as I mentioned at the beginning, liquid phase reaction, it means you need to change the valid phases here to liquid only, right? Oh, sorry, to liquid only. And then the reactor volume, we're given the volume to be 1 meter cube from the question. So we can make it 1,000 liters or we can just make it 1 meter cube. So meter cube usually presented with cubic meter, CUM, cubic meter. So we'll have that down. Then the kinetics, the same thing we did previously. We'll click on new, the type of reaction, we'll choose power law, and then we can click on OK. So I'll now go to specifying the reaction. Now, this is a reversible reaction. So this time, the reaction is going to look a little bit different, right? If we have A forming B, now we are going to have our R to be equal to a minus K Ca minus Cb over maybe a Ke. Please, do we remember these things? Right? So we'll have it in this form. Is that fine? For a reversible reaction. We can break it up into two. We can break it up into the forward reaction and then the backward reaction. So Kca would be the forward reaction. So we can say that for the forward reaction, we'll label it as Rf minus Rf. So that will be equal to Kca. And then we'll have minus Rb to be equal to K over Ke Cb. Please, is that okay? I hope you get what we
Yes,
are
please.
doing.
Yes.
Yes, please.
Okay. I can see you guys really learned the reaction engineering. So I don't need to really go into too much detail, right? Anyway, so the K value, remember, this was the K knots we had. We said we have to change it to per second to be consistent with Aspen, right? We're given the activation energy, we're given the T knots, so we can easily do this. So for the K knots, this is what we are going to be using. We have our activation energy, we have our T knots. That's for the first reaction, the forward reaction. So they are using K1 to represent the K for the forward reaction, right? And those are the details the question gave us. It gave us the K, where is it? Where was it? Where was it? Hey, I can't seem to find it anymore. It gave us the K, right, at 360 Kelvin. So we can work with it from there. And it gave us the activation energy as well. Okay. Now for the reverse or for the backward reaction, our K is going to be K over Ke. So we can see that from here. The K we are going to have, or K2, what we are using representing as K2 is K over Ke, right? And that is where we now see this expression. So they take the K value and then the Ke value and then they divide them. We have to simplify it to get one expression. Now the problem with this is we have two T naught values. We have 360 and 333 because they were at different, or we did their specifications at different temperatures. So in order to make everything consistent, what they did was that they found an expression for Ke also at 360. So you can put in a temperature of 360, use it to find what Ke will be there, and then find a new expression for the Ke, right? And that's what we see over here. So you can just put in your 360, you get to your new, maybe, let's call it Ke1, right? So maybe Ke naught is 3.03. When you put in 360, you get Ke1, that is the 2.5134. Then you can use Ke1 with T1 to write an expression for it, for what Ke should be. Then if we should simplify the math over here, we'll end up with the expression in this final form. So this is for the backward reaction, the key for the backward reaction. So now let's specify all the reactions and then specify their constants. For the forward reaction, we have N-butane. Was it N-butane going to I-butane? Yeah, N-butane going to I-butane. Coefficient is 1, exponent is 1, because Ca is to the power 1. And then the product is I-butane, coefficient is 1, exponent is 0. So that's for the forward reaction, right? You can specify a second reaction separately, but we are doing everything under R1 and it's fine. Aspen will be able to handle it. So for the second reaction, this time is the reverse. So I-butane now becomes the reactant, coefficient is 1, exponent is 1, and then N-butane becomes the product in the reverse direction. So we'll have these details. Now we can come to the kinetics tab. We are already in the liquid phase, so we keep it as that, and we are keeping it at the reactor volume. We're not giving much information about the catalyst, so we'll keep it under reactor volume. Now for the forward, remember I mentioned that you can see the two different reactions here. So we are on the forward reaction now. The K we had, or that we are using, was 0.0086. So put that in 0.0086. The E was 65.7, the activation energy. Please don't include the minus. Aspen caters for the minus. Right? If you should put in the minus, it will give you a warning. Right? So don't put in the negative. And then the T naught was 360. We are working on a concentration basis, so that's fine. Then for the reverse reaction, the K naught was 3.437 E minus 3, or times 10 to the power minus 3. The E is 134.7. Oh, this is kilojoule per mole. I think. I hope I changed it for the first one. And then the T naught is 360. So let me confirm the units. It's supposed to be kilojoule per mole for all of them. Yeah, this is kilojoule per mole. And I know because from the question, we're given the activation energy here in kilojoule per mole. So the units are very important. Okay, so once we are done with this, we can run it. Okay, we have our results available. So let's check them out quickly. So the block results. So we see our outlet temperature. Did we make it adiabatic? We made this adiabatic here. The inlet was 330. Okay, so the outlet was the same temperature. So we have these details here. And then we can look at the stream results. So the mole flows. So we see that a very small amount of iButane was formed. Let me see. That was a very, very small amount. Okay, just a minute. I think we got all the specifications. Yeah, the temperature should have been different if it was adiabatic. Okay, let's give it some time to load and then we'll pick it from there. Everything is correct here. Everything is correct here. I have to check this values again. Oh, okay, could also be the property method I selected. That's fine. So when it's done running, I'll confirm it. But while it's running, are there any questions? Any questions so far? Okay, so there are no questions. So we have two more examples to try. I wanted to find out, think I wanted to find out when you'd be writing your exams so that I would know how meetings would be like. Oh, this is really taking long.
Uh, Oteku, we'll be starting our exams coming Tuesday.
Oh, this coming
So
Tuesday.
yes,
When
please.
is when is it ending?
I think everyone has their ending periods, but we would end ours on the 25th.
Okay, okay, okay. So it means that okay. I was thinking about the assignments and meetings on the 20th. Oh wow. Okay, so then okay, I'll put something together. I would discuss something with Samuel and then we'll put something together. We'll see how we can go about things.
Okay, okay.
Oh, I'm wondering why I'm not getting the values I'm looking for. So I think we would end our discussion on this for today. Let me just make sure that my specifications were not wrong. 20 bar 0. Yeah, the volume is fine. The volume is fine. Let me check the kinetics again. To iButane. So we have, uh, yeah, that's all fine. And then the other one was iButane to N-butane. Yeah, it's also okay. Oh, Kelvin. Okay, okay, okay. Let's see, not was supposed to be in Kelvin. That was my mistake. Okay. Ah, you see what little little mistakes can do. Okay, so now let's check the stream results. Ah, okay. Now we are getting something significant being formed. So yeah, that's how these things are. So the other examples we have a packed bed reactor. Is there a question? We have a packed bed reactor, and then we would have to account for a few things. This one is actually a very interesting question. I really like this one because you have to do a little bit of calculation here and there, some more fraction stuff and all of that. So I actually like this question a lot. But what I'll do is that because you guys are going to be doing starting your exams on Tuesday, the plan I have in mind is that we would record lessons, like maybe portions of it for the different things that are left. And then I'll give you maybe a project or assignment. I would put it together and show it to Doc first. And then if he approves of it, you guys can work on it during your vacation. I think that should be good enough. So I'll try to put material together for you so that by the time you are done with your exams, you can just go back to it, try out the projects, and then you can still learn alongside. Would that be fine?
Yes, please. I think that would be a
Yeah,
very good idea.
fine.
Okay. So then I think we can end for today. I've done all the simulations for all the examples. So I'll send all of them to you so that if anyone even feels like trying out the other ones on their own, at least they will still have the simulations already there. So that's what I would do as well. So we'll just end our discussion here for now. And then I'll see you guys another time. Thank you for your time. All the best in your exams.
Thank you very
Thank you
much
very
as
much.
well. God bless
Thank you.
you.
Amen.